When a patient arrived in my clinic with a hemoglobin A1C of 11.2%, her physician had already scheduled her for insulin initiation. 6 months later, her A1C measured 5.9%, a reduction of 5.3 percentage points achieved through the strategic elimination and replacement of 3 specific food categories. No medication changes, no surgical intervention. 3 foods. I am a professor of genetics at Harvard Medical School, where my laboratory investigates the molecular mechanisms underlying metabolic dysfunction. What I witnessed in this case challenges the prevailing narrative that type 2 diabetes represents an irreversible, progressive condition requiring lifelong pharmaceutical management. Today, I'm sharing the exact 3 food modifications that produce this transformation, the molecular mechanisms explaining why these changes exert such profound effects, and the measurable biomarker improvements I've documented. The molecular reality of elevated A1C. Before examining the interventions, understanding what an A1C of 11.2% represents at the cellular level proves essential. Hemoglobin A1C measures the percentage of hemoglobin proteins that have become glycated, permanently bound to glucose through a non-enzymatic reaction called the Maillard reaction. Since red blood cells circulate for approximately 90 to 120 days, A1C provides a weighted average of blood glucose exposure over the preceding 3 months. An A1C of 11.2% corresponds to an estimated average glucose of approximately 275 milligrams per deciliter. At this concentration, glucose molecules continuously attack proteins throughout the body. Advanced glycation end products accumulate in the vasculature, kidneys, retinas, and peripheral nerves. Research published in the New England Journal of Medicine demonstrates that every 1% reduction in A1C correlates with a 37% decrease in microvascular complications and a 14% reduction in myocardial infarction risk. The 5.3 percentage point reduction this patient achieved translates to profound risk modification across every organ system. The critical insight driving my approach: elevated A1C does not represent a glucose problem. It represents an insulin signaling problem. Glucose accumulates in the bloodstream because cells have become resistant to insulin signal to absorb it. The 3 food modifications I implemented target insulin resistance at its molecular roots. Food elimination number 1: seed oils and industrial vegetable fats. The first modification involved complete elimination of seed oils: soybean oil, corn oil, canola oil, sunflower oil, safflower oil, and cottonseed oil. This single change addresses what I consider the most underappreciated driver of insulin resistance in the modern diet. The molecular mechanism. Seed oils contain extraordinarily high concentrations of linoleic acid, an omega-6 polyunsaturated fatty acid. Soybean oil, the most commonly consumed fat in the Western diet, contains approximately 54% linoleic acid. When consumed in typical modern quantities, linoleic acid accumulates in cell membranes throughout the body. Research published in Cell Metabolism has elucidated the precise mechanism. Cell membranes require specific fatty acid compositions to maintain proper fluidity and receptor function. When linoleic acid displaces other fatty acids in adipocyte and myocyte membranes, insulin receptor conformation changes. The receptor still binds insulin, but downstream signaling becomes impaired. The consequences cascade through multiple pathways. GLUT4 transporter translocation to the cell surface diminishes. Glucose uptake decreases. The pancreas compensates by secreting more insulin. Hyperinsulinemia develops. Eventually, even maximal insulin output cannot overcome the resistance. Additionally, linoleic acid undergoes oxidation to form reactive aldehydes that directly damage mitochondrial function. Studies in the Journal of Biological Chemistry demonstrate that these oxidation products specifically inhibit pyruvate dehydrogenase, the enzyme complex linking glycolysis to the citric acid cycle. Perhaps most concerning, linoleic acid has a biological half-life of approximately 680 days in adipose tissue. The seed oils consumed today continue disrupting metabolism for nearly 2 years. Implementation: I instructed this patient to eliminate all foods containing seed oils, which required substantial dietary restructuring. Seed oils permeate the modern food supply. Restaurant cooking, packaged foods, salad dressings, mayonnaise, bread, crackers, and virtually all ultra-processed products. Replacement fats included extra virgin olive oil for cooking below 375 degrees Fahrenheit and raw applications, grass-fed butter and ghee for higher temperature cooking, avocado oil for high heat applications, coconut oil for baking, animal fats from pastured sources. The patient prepared all meals at home for the first 90 days, using only these approved fats. Documented effects. Within 8 weeks, this patient's fasting insulin, which had measured 42 micro-UIU milliliter at baseline, decreased to 18 micro-UIU milliliter. Her HOMA-IR dropped from 11.3 to 4.2. The improvement in insulin sensitivity preceded the full A1C reduction, demonstrating that insulin resistance correction enables subsequent glycemic normalization. Food elimination number 2. Refined carbohydrates and high glycemic starches. The second modification targeted refined carbohydrates, white flour products, white rice, breakfast cereals, crackers, pastries, and added sugars. This category extends to many foods marketed as healthy: whole wheat bread, instant oatmeal, fruit juices, and granola bars. The glycemic variability mechanism, the damage from refined carbohydrates, extends beyond their contribution to average glucose elevation. Research published in Diabetes Care demonstrates that glycemic variability, the magnitude of glucose excursions throughout the day, independently predicts complications even when A1C remains controlled. When refined carbohydrates enter the digestive system, their rapid absorption creates glucose spikes that overwhelm the pancreatic beta cell response. Glucose may rise from 100 milligrams per deciliter to 220 milligrams per deciliter within 30 to 45 minutes. The pancreas releases a delayed, exaggerated insulin bolus. Blood glucose crashes. Counter-regulatory hormones surge. The cycle repeats. This volatility activates multiple pathological pathways. Studies in circulation demonstrate that acute hyperglycemia induces endothelial dysfunction within hours. Research in Nature Medicine shows that glucose spikes trigger inflammatory cytokine release through NF-kappa B activation. At the mitochondrial level, rapid glucose influx overwhelms the electron transport chain. Electrons leak, generating superoxide radicals. Oxidative stress damages mitochondrial DNA and compounds insulin resistance. The hepatic mechanism, refined carbohydrate overconsumption, drives hepatic insulin resistance through a distinct pathway. Fructose and glucose, delivered rapidly to the liver, exceed oxidative capacity. The liver converts excess carbohydrate to fat through de novo lipogenesis. This newly synthesized fat accumulates within hepatocytes. Non-alcoholic fatty liver disease develops. Research published in Gastroenterology demonstrates that intrahepatic fat directly impairs insulin suppression of hepatic glucose output. The liver continues releasing glucose even when blood glucose is already elevated. The patient I'm describing had evidence of hepatic steatosis on ultrasound at baseline, a finding present in over 70% of individuals with type 2 diabetes. Carbohydrate sources were restructured. Non-starchy vegetables became the primary source: leafy greens, cruciferous vegetables, peppers, tomatoes, zucchini. Berries in limited quantities, half cup daily. Legumes in moderate portions, half cup cooked. Resistant starch sources, cooled and reheated potatoes, cooked and cooled rice in small quantities. Eliminated entirely. All white flour or wheat flour products, all breakfast cereals and bread, all fruit juices and dried fruits, all added sugars, white rice, instant oatmeal, crackers, chips. Total daily carbohydrate intake was targeted at 50 to 75 grams, approximately 10 to 15% of calories, compared to the 45 to 65% recommended by conventional guidelines. Documented effects. Continuous glucose monitoring revealed dramatic improvements. Pre-intervention, this patient experienced glucose excursions ranging from 65 milligrams deciliter to 340 milligrams deciliter within single days. By week 12, glucose remained between 85 to 145 milligrams deciliter throughout entire 24-hour periods. Time and range improved from 31% to 94%. Her liver ultrasound at 6 months showed complete resolution of hepatic steatosis. ALT normalized from 67 U per liter to 22 U per liter. Food addition number 1, high-quality protein with every meal. The third modification involved ensuring adequate high-quality protein at each eating occasion. This addresses the often overlooked role of protein in glycemic regulation. The incretin mechanism protein consumption triggers release of incretin hormones, GLP-1 and GIP, from enteroendocrine cells. Research in cell metabolism demonstrates that these hormones potentiate glucose-stimulated insulin secretion while suppressing glucagon release. When protein accompanies carbohydrates, GLP-1 release enhances insulin secretion and timing, blunting postprandial glucose excursions. GLP-1 also slows gastric emptying, reducing glucose delivery rate to the intestine. Notably, the medications semaglutide and tirzepatide are synthetic GLP-1 receptor agonists. The protein-first approach harnesses endogenous incretin secretion to achieve similar effects through dietary means. The muscle metabolic axis. Skeletal muscle represents the primary site of insulin-mediated glucose disposal, accounting for approximately 80% of postprandial glucose uptake. Research in diabetes demonstrates that muscle mass directly correlates with insulin sensitivity. Greater muscle mass provides greater glucose sink capacity. Adequate protein intake supports muscle protein synthesis and prevents sarcopenia. Studies in the American Journal of Clinical Nutrition show that protein intakes of 1.2 to 1.6 grams per kilogram body weight optimize muscle protein synthesis, significantly higher than the 0.8 grams per kilogram RDA. The thermic effect. Protein exhibits the highest thermic effect of food. Approximately 20 to 30% of protein calories are expended during digestion, compared to 5 to 10% for carbohydrates and 0 to 3% for fats. Research in nutrition and metabolism demonstrates that high-protein diets increase resting metabolic rate by 80 to 100 calories daily, compared to isocaloric lower-protein diets. Implementation. Protein targets were established at 1.4 grams per kilogram body weight daily, distributed across 2 to 3 meals within an 8 to 10 hour window. For this patient at 187 pounds, this translated to approximately 120 grams daily. Emphasize sources. Wild-caught fatty fish, 3 to 4 servings weekly. Pastured eggs, 2 to 3 daily. Grass-fed beef and lamb, 3 to 4 servings weekly. Pasture-raised poultry, 2 to 3 servings weekly. Full-fat Greek yogurt, 1 cup daily. Each meal contained 35 to 45 grams of protein, consumed before any carbohydrate component. Documented effects. Lean body mass increased from 98 pounds to 108 pounds over 6 months, a 10-pound gain despite overall weight loss. Resting metabolic rate increased from 1,340 to 1,520 calories daily, a 13% improvement. The remarkable efficacy of this protocol emerges from synergistic interactions. Each modification addresses a distinct driver of insulin resistance, and their combined effect exceeds the sum of individual contributions. Seed oil elimination removes chronic inflammatory stimulus and restores membrane fluidity necessary for insulin receptor function. Refined carbohydrate elimination reduces glycemic variability and hepatic fat accumulation, allowing the liver and pancreas to reset. Adequate protein stimulates endogenous incretins, preserves metabolically active tissue, and increases energy expenditure. Research from my laboratory demonstrates that metabolic interventions exhibit nonlinear dose-response relationships. Partial implementation produces partial results. Complete implementation enables the metabolic system to achieve new homeostatic set points impossible with isolated interventions. The 6-month protocol, Month 1, Foundation. The patient eliminated all seed oils and refined carbohydrates while establishing protein targets. Meal preparation occurred exclusively at home. A continuous glucose monitor provided real-time feedback. Daily structure. Morning, black coffee. Delay first meal until genuine hunger, typically 10 to 11 a.m. First meal, 40 grams protein, non-starchy vegetables cooked in olive oil, half cup berries. Second meal, 45 grams protein, large salad with olive oil dressing, steamed vegetables. Optional third meal, 35 grams protein, vegetables, small portion legumes. Eating window, 8 to 10 hours. Hydration, 80 plus ounces water daily. Months 2 to 3. Optimization. With glycemic patterns stabilizing, a 10 to 15-minute walk after each meal was implemented. Research in diabetes care shows post-meal walking reduces glucose peaks by 30 to 50%. Light resistance training was introduced. 3 sessions weekly focusing on compound movements. Months 4 to 6. Maintenance. Restaurant dining was gradually reintroduced at compatible establishments. Home cooking remained the foundation. Measured results. Glycemic markers. Marker baseline, 6 months. Hemoglobin A1C, 11.2%, 5.9%. Fasting glucose, 234 mg per dl, 94 mg per dl. Fasting insulin, 42 micro-IU milliliter, 11 micro-IU milliliter. HOMA-IR, 24.2, 2.6%, 94%. Metabolic markers. Marker baseline, 6 months. Triglycerides, 312 mg per dl, 98 mg per dl. HDL cholesterol, 34 mg per dl, 56 mg per dl. hs-CRP, 8.4 mg per liter, 1.2 mg per liter. ALT, 67 U-liters, 22 U-liters. Metric, baseline 6 months. Body weight, 187 pounds, 156 pounds. Waist circumference, 42 inches, 33 inches. Lean body mass, 98 pounds, 108 pounds. The patient reported resolution of polyuria, polydipsia, and fatigue within the first month. She discontinued the insulin prescription she had been given, but never started. Common questions. Can these results be achieved while on medications? Yes. However, medication adjustments are often required as insulin sensitivity improves. Patients on sulfonylureas, insulin, or SGLT2 inhibitors require monitoring for hypoglycemia. Work with a physician who can titrate medications as metabolic function normalizes. How long before A1C improvements appear? A1C reflects the preceding 90 to 120 days, with greater weighting toward recent weeks. Glucose improvements occur within days. A1C requires 2 to 3 months to reflect changes. I typically recheck at 3 months, expecting 2 to 3 percentage point reductions. Is this safe for type 1 diabetes? Type 1 involves autoimmune destruction of beta cells and absolute insulin deficiency, a fundamentally different condition. While these principles may improve stability and reduce requirements, insulin remains essential. This protocol was developed for type 2 diabetes. What about fruit? Berries are included for polyphenol content and low glycemic impact. High-sugar fruits are eliminated during intervention. Once metabolic function normalizes, moderate whole fruit may be reintroduced based on individual response. How strict is seed oil elimination? During the initial 90 days, strict elimination optimizes results. After that period, occasional unavoidable exposure is unlikely to derail progress. But home-prepared meals should remain the foundation. The fundamental principle: This case demonstrates a principle my research has reinforced. Type 2 diabetes is not a disease of glucose dysregulation requiring glucose-lowering medications. It is a disease of insulin resistance with identifiable, modifiable causes. When seed oils disrupt membrane function, when refined carbohydrates overwhelm hepatic capacity, when protein inadequacy allows muscle wasting, insulin resistance develops as a predictable consequence. Remove these causes, and the body's capacity for self-regulation reasserts itself. The three modifications I described address root mechanisms. They require no pharmaceutical intervention, no surgical procedure. They require knowledge, commitment, and consistency. An A1C reduction from 11.2% to 5.9% represents metabolic transformation at the cellular level, restoration of insulin signaling, reversal of hepatic steatosis, regeneration of mitochondrial function. 3 food changes, 6 months, a second chance at metabolic health. Disclaimer: this content is for educational purposes only and does not constitute medical advice. The case described represents an exceptional response. Individual results vary. Anyone with diabetes should work closely with their healthcare provider before modifying diet or medications. Rapid improvements in blood glucose may require medication adjustments to prevent hypoglycemia.